On average, the United States, as well as the rest of the world, has been warming, particularly in the last 50 years. Scientists have determined that much of this comes from heat trapped by greenhouse gases emitted through human activities, such as the use of fossil fuels. Overall, the average warming in the U.S. has been about 1.7 degrees Fahrenheit, or 0.95 degrees Celsius, since the late 1800s. Recently, the National Climatic Data Center issued its new Climate Normals data, 30-year averages of climatological variables such as temperature and precipitation that serve as reference points. These are used for everything from energy use projections to choosing crops and planting times. This graphic depicts the differences between the new normal, which averages annual temperatures for the period from 1981 to 2010, and the previous 30-year average that ended in 2000. The graphics indicate that on an annual basis, every state has experienced warming in both the minimum temperatures, shown on the left, and the maximums, on the right, although some have warmed more than others. Average annual lows are now warmer, particularly in the desert Southwest, the Northeast, and the Great Lakes. Daytime highs have increased the most in the Southwest, Rocky Mountains, and Michigan, Wisconsin, and New Jersey. This temperature increase has had a wide variety of effects. For example, warmer temperatures lead to more moisture in the atmosphere, which has increased precipitation over much of the U.S. However, there are important regional and seasonal differences. Warmer winters mean that, on average, less winter precipitation falls as snow and more as rain in the northern part of the country. This can cause water shortages in places that depend on winter snowpack to supply the majority of their water resources, and it can also adversely affect winter recreational activities. Increasing temperatures can also affect the timing of spring or early summer runoff. For many western rivers, the initial pulse of water from snowmelt is occurring about 2 to 3 weeks earlier. Although some of these changes can be explained by natural variability, it appears that most of the shift is probably due to global warming. The reduction in snow cover and earlier snowmelt likely means a longer snow-free period during the warm season, which may increase drought severity and wildfire risk, and decrease soil moisture and long-term water storage. Temperature also affects ecosystems in a number of ways. As shown in this graph, the growing season is now about 9 days longer in the eastern U.S. and 13 days longer in the West. This longer growing season could be a good thing in many cases for farmers, but there are also downsides because the growing season is also extended for weeds, invasive species, and allergens. And some crops, like many varieties of fruits, require a certain number of hours at colder temperatures, so warmer temperatures could reduce their productivity. Such changes can also play havoc with both agricultural and natural ecosystems. One example comes from a study of glacier lilies near Crested Butte, Colorado, which are pollinated by hummingbirds and bumblebees. Over the last couple of decades, scientists have noted a reduction in pollination because the flowers are emerging earlier than the arrival of the pollinators, which could put the plants at risk for extinction. Climate systems, ecosystems, and even human systems are interrelated in many complex ways, so it's not surprising that a change in one of them causes ripples through others. This graphic shows just a few of the regional changes that have already been observed. If greenhouse gases continue to accumulate in the atmosphere, we can expect even more impacts. Some of these can be beneficial, but many can be problematic, and the effects can vary from location to location. To help determine what might happen in different areas, scientists turn to computer models. Relating global climate change projections to regional or even local effects is critical for making policy and investment choices that can reduce the potential for future adverse climate impacts. However, it is not simply a matter of running a global climate model and looking at the results for a specific location. To understand why, you need to first understand a bit about global climate models. Global climate models simulate Earth's chemical and physical processes to produce estimates of temperature, precipitation, and other parameters. These models are used to study Earth's past climate changes, and they provide an important tool for checking our understanding of how climate processes work. Since we don't have a spare Earth to experiment with, models also give us a way to conduct tests to see how the climate might change under various possible future conditions. In other words, models are a big part of how we understand climate science. Global climate change models reveal large-scale patterns of change, such as the temperature projections shown here, which are based on particular assumptions of future greenhouse gas emissions. Global models are useful for understanding broad features of climate change, but are less useful for answering questions about what might happen in smaller regions. This is because global-scale models could never perform calculations quickly enough if they included all the detailed features and processes at the surface and in the atmosphere. To reduce the number of calculations, they break the surface and atmosphere into grid cells. As a result, topographical features are smoothed or averaged over relatively large distances, and regional or local features that often determine the finer structures and weather patterns are missed. So, for example, the model results in the left image get the broad features correct, but miss many details that show up in the observations in the right image. This is particularly true in the western U.S., where there is more varied topography. Global climate models can also miss other influences, such as those caused by the interface between sea and land. A technique known as downscaling takes global climate model output and uses it to provide information closer to the local level. Scientists use two basic methods, dynamical downscaling and statistical downscaling. So in this example, a regional climate model, an example of dynamical downscaling, gives results that produce more realistic local scale features that better replicate the observations. In dynamical downscaling, scientists nest a regional climate model, shown in the center of this figure, within the output of a larger global-scale climate model, indicated by the larger pixels on the edges. The nested regional climate model takes meteorological, oceanic, and land surface data generated by the global climate model and makes a regional projection. Because regional models have a more limited scale, they can be run at much higher resolution, as shown by the smaller pixel sizes, than can be achieved by global models. Nested regional climate models are improving every year and can even produce realistic depictions of weather features such as this simulation of a possible future hurricane hitting the Gulf Coast. Some researchers downscale the results further by also using weather scale models that can simulate individual storms. While these results are not intended as forecasts years in the future on a specific day, the model's ability to produce realistic weather indicates they can simulate features that affect broader weather patterns. Researchers then use simulations of specific events to establish statistical trends in such things as frequency of hurricanes per year over a multi-decadal period. However, dynamical downscaling has its challenges. For example, small errors in the global climate model may amplify inside the nested domain and become major errors. Another weakness is the lack of productive crosstalk between the regional climate model and the global one. The regional model can theoretically provide the global one with feedback, increasing overall accuracy, but this also increases the computing requirement substantially. The second approach, statistical downscaling, takes advantage of statistical relationships between regional climate and global climate. That is, scientists may notice that when the global climate does A, the regional climate responds by doing B some percentage of the time. By developing a list of these kinds of statistical associations, scientists can input the conditions projected by global models into regional statistical downscaling systems to predict how the regional climates will respond to future global temperatures or greenhouse gas concentrations. It is important to note that it may be difficult to develop statistical relationships in remote or topographically complex areas, especially ones where long-term weather records are not available. The climate in a valley is different from that higher up in rugged terrain, and it can also differ on the sunny side of a mountain versus the shaded side. Yet because of limitations in computing power, these dramatically different features could all lie within a single global climate model grid cell, for which the model would simulate a single value of precipitation or temperature. Despite these challenges, the information that can be gleaned from downscaling can provide valuable input for planning and adapting to both periodic climate variability and long-term climate change. Scientists are even beginning to study climate change effects on relatively small-scale, extreme weather events, such as the hurricane shown in this simulation. Future results will undoubtedly improve as modeling techniques progress, new observations provide additional data, and research advances our understanding of the climate system. Although the field of regional climate modeling is still maturing, It can take governments years to approve, fund, and implement adaptation and mitigation measures. With no solid worldwide plans to reduce human emissions of greenhouse gases in the near future, many U.S. regions and states have begun to use the best information currently available from climate science as inputs for assessments of likely impacts and strategies for dealing with them. For example, the second California assessment, issued in 2011, used downscaled climate and sea level rise scenarios from 6 global climate models run with 2 different greenhouse gas emissions scenarios. The models provided projections of warming, precipitation, and sea level rise. The model results were then given to experts from other fields who performed their own modeling and analyses to assess climate change impacts on various California sectors, such as water resources, agriculture, wildfires, public health, and energy. These experts also provided some guidance about possible strategies to reduce adverse impacts. Of course, future climate change impacts will vary from one location to another. Some of the expected regional impacts are shown here. The magnitude and timing of these impacts depend on many factors, including natural variability. In addition, the rate at which we are adding greenhouse gases to the atmosphere will play an important role.